Welcome to this lecture series in linear algebra. In this lecture, we'll learn the real spectral theorem. And basically, all we need to know is what is a self-adjoint operator and the fact that every self-adjoint operator has an eigenvalue. So what is a self-adjoint operator? A self-adjoint operator is an endomorphism on an inner product space, let's call it V, such that it is equal to its own adjoint. Okay, and we showed that every self-adjoint operator has an eigenvalue regardless of whether the vector space is real or complex. Okay, here are some problems for practice. And now let us move on. So we need a small lemma before we state and prove the main theorem. So fix an inner product space and fix a self-adjoint operator on it. And if U is T invariant, then U perp is also T invariant. Okay. So it's really a one-line proof. So let U prime be in U perp, arbitrarily chosen. We want to show that Tu prime is also in U perp, which is basically the definition of invariance. Okay, so let's do it. So to do that, we fix an element in space U and consider this product. We consider this inner product. We want to show that this is 0. That is what it means to say that this is in the orthogonal complement of U. So what is this? By the property of the adjoint, it's equal to this, but then now since T is self-adjoint, it is equal to that. But since U is in U and U prime is in U perp, this is 0. And that finishes the proof. So it's a very simple lemma. And now let us continue. So here is the real spectral theorem. Fix an inner product space and an endomorphism on it, which is self-adjoint. Then there is an orthonormal basis of V consisting only of eigenvectors of T. Okay. So if V were a complex inner product space, self-adjointness already implies normality, and the result follows from the complex spectral theorem. So we may assume that V is real for this argument, but the argument will not even care about that assumption. So let's just prove it. Okay, now since we know that every self-adjoint operator has an eigenvalue, we may pick be a non-zero eigenvector corresponding to some eigenvalue, call it lambda. So that means Tu is equal to lambda U, where we need to remember that U is non-zero. Alright, so therefore, if we say capital U is the span of small u, then U is T invariant. Right? Since U is an eigenvector, the span of U is T invariant, and hence, by the previous lemma, U perp is also T invariant. Right? And here is a small exercise, which I write as a claim. Since U perp is T invariant, this is of course an endomorphism on U perp. This is also self-adjoint. This is a trivial statement. You can argue it in one line. Okay, now, by arguing inductively, by induction, on the dimension of domain space. So I will explain this statement. We wanted to prove this statement. So it is, first we prove it for dimension 1. Suppose we establish this statement for the case when the dimension of V is 1, in which case this is a trivial statement. So having established that, we may assume that we may start with a vector space of smallest possible dimension for which one can find a counterexample to this proposition. Okay, and this smallest possible dimension necessarily will be greater than 1 because the statement is true for one-dimensional vector spaces. Okay, and when we write this statement, this is what we mean. I mean, we have argued in this fashion various times, and you can also look at my primers on the well-ordering principle available in the Kickstart playlist to better understand this point if you are not clear. So basically, we are inductively arguing over the dimension of the parent space. Right, so let me continue. So by induction on the dimension of the domain space, we may assume that, or rather we know, there is an orthonormal basis of U perp. Let's give it a name. Basis B, I don't know, B, it doesn't even matter, just the vectors matter. Orthonormal basis. I'm starting the index with 2 deliberately, consisting only of eigenvectors of this guy. Alright, and now define E1 as normalization of U. So this U is that U, and here is something that I leave you to check. Then this is an orthonormal basis. That's it. That finishes the proof. So this induction step one should follow. Start with a smallest dimension vector space which furnishes a counterexample to the proposition. Alright, this vector space must necessarily have dimension at least 2. Find an eigenvector in that space, non-zero eigenvector in that space, take the span of it, and then pass to the orthogonal complement. It turns out that the restriction to this orthogonal complement is also self-adjoint. That's a trivial fact. Now, since the dimension of U perp is strictly smaller than the dimension of V, the statement here holds for this particular space, and hence we can find an orthonormal basis consisting only of eigenvectors of this guy, and we just append E1 to it to get an orthonormal basis of the original vector space consisting only of eigenvectors of the original endomorphism. That's it, and that finishes the proof. So maybe I'll just make one small remark about what is going on. An orthonormal basis consisting of only eigenvectors in 2 dimensions looks like this. So this is some vector, let me call it V1 maybe, not E1, otherwise you get confused. So what does T do to such a basis? These are 2 orthonormal, 2 orthogonal vectors of unit norm. And suppose they are both eigenvectors of some transformation T, then it will scale this guy and scale that guy, maybe with different dilations. So basically, with the correct perspective on the vector space, the endomorphism looks particularly simple. If you take some other basis, the endomorphism may look much more complicated. But with the correct perspective, if you rotate your head correctly, you will find that the endomorphism is not really doing much. So yeah, so that's it. And with that, I want to end this. As usual, like, comment, share, subscribe, and I will see you next time.